All right, so I'm Sanjiv Singh. For anybody who doesn't know me, I've been here forever, lifer, still here. A little bit on vacation, so to speak. But I think we've had enough of ground vehicles, right? I think we want to, like, it's just too much. My God. You know, we told the story a few times. Sorry, guys. You know, great stuff, but let's think about something else. So I, in fact, have been here for so long. I got to Carnegie Mellon in August of 1985 to work on that blue vehicle you've seen before. I got here 2 weeks before the vehicle actually arrived as a shell, and then my job was to get the signals from the back, the racks of computing, to talk to the steering and the transmission. So that was my first job working on NavLab. And so about a year later, it was moving at about walking speed. And so, 40 years later, we're still at it, the whole thing, machines understanding the environment, reacting to the world as discovered. And now what we've got is one of the latest helicopters in the world. It's a state-of-the-art helicopter that carries 5,000 pounds, can fly 300-400 miles. We're turning that into a robot. This is a new program of record, and at the U.S. Marine Corps, and we're about doing that. So there's a big gap there, right? So let's talk about what's happened in between. In between, there were some really great programs and some really great world's first, and they're worth talking about. So DARPA, of course, usual suspect, working early. They were looking for something that would fly at 30 feet. Previously, aircraft flying high, ground vehicles on the ground. Can you have something fly in between buildings, trees, wires, that sort of thing? And so world's first helicopter, and actually there were two programs, they were both from Carnegie Mellon. One was led by Omid's team, and one was led by my team. We were working with two different primes, and we were at Fort Benning, in a kind of a fly-off kind of situation. But, good work coming out. Sebastian did some of the great early work in that area. Some of the people who made this thing into something, aircraft, maybe one of the first aircraft that could fly at low altitude in complex environments. We got a program from the Army Combat Medic Program. They were looking for an aircraft to fly to the location of a casualty and then land by itself and then be able to fetch that thing. There was no casualty involved at that time, but the idea is, can you have a helicopter fly to a place that it has never been to before, or find a safe place to land? So when we just did the program by renting the helicopter from Boeing, adding some sensors to the front, computing in the back, just like we did with NavLab, right? And think about it. And then somebody said, wait, has anybody ever flown a full-size helicopter before? It never occurred to us to ask that question, but turned out it was the first time anyone had flown a full-scale helicopter. So that's about the time this started becoming big. Afghanistan was looming, or actually in progress. Deliveries by road were treacherous. They were taking hours or days in some cases. The roads were mined. The idea was, hey, maybe you can fly. And so we got together a small company, wrote a proposal for that. And our idea was, well, we win, we'll go. And then we won. So we had to start the company, had to actually do something. So, I have to credit this at this point here, right? The one thing that I got from 1985 to now is that, I credit this to Red, is that we never asked the question, is this something we should be doing? Or could we do this? Is this something we do? By the way, remind me where the aerospace department is at Carnegie Mellon, right? We never thought about that, never worried about it. And that's, I think, the spirit that got all of these things happening here. And so, we started the program and started the company in 2012, worked our asses off. It was like 100-hour weeks. Our motivation was we just had to beat the world's largest defense company. And, they were working 35-hour weeks. And so we knew we'd win. And so, in fact, we did. We got on to the rest of it, and we flew a Huey Vietnam era Huey that had been converted fly-by-wire, and we flew that at Quantico, and it was the first autonomous helicopter operating in the stereo environment. So, I think you saw a lot of ground vehicles, some really great work, which is actually the basis of what we've been doing for a long time. And so I just want to take a moment to acknowledge that the world's first an autonomous aircraft of this type happened right here at Carnegie Mellon. And that's like something to say. Thank you, Red. Thank you for the spirit. Thank you, Raj, for having this kind of thing. I remember in the early going, somebody asked, what kind of people do we hire in robotics? Is this really a robotics? And Raj said, well, let's hire them and we'll figure out if it's robotics or not. Can you think about that? There was no other department. They were like, yeah, psychology. Is the guy a psychologist? No. Okay, let them get a joint appointment somewhere else. Okay, we didn't do that. And so, more of that. Okay, so look, here's the question, right, that I want to ask is okay, is this more of the same? Some things are different, right? Some things actually got easier, right? One day when I was thinking to the middle of this, I hadn't seen Tony for a while. He came up to me, he goes, you're cheating. And I said, yeah, I get it. I totally get it. You have an extra dimension. You have more options to maneuver, fewer obstacles. What's wrong with this picture, right? No cul-de-sacs, no potholes, or as we like to call them in this room, negative obstacles. If I said negative obstacles to anybody else, they would be like, what? Okay, negative obstacles, no negative obstacles. You don't have to figure out if it's vegetation, or is that a rock? Is there a rock inside the vegetation? No, you just stay away from all of it, right? So some things got easier. But there's trouble in paradise, right? You need a lot more power, so weight is everything. Everything has to be aerodynamic. You can't just pull over, right? The energy requirement for when you're stopped is very close to zero in a ground vehicle, but it's not the same in an aircraft. So, aerodynamics matter a lot. And so, yeah, that part, no aerospace background, that kind of hurt. The first few times, we're like, what? You need an FAA clearance to put a GoPro on the outside of a Cessna or something? How does that work? We had to learn all that. Okay, we did that. Also, here's the part, right? Higher potential for damage. It's harder to contain these things. You build a robot city kind of thing with some fences and you do whatever you want. The robot's not getting away. Uber had this test site there, and nobody saw it, and nobody was worried that those ground vehicles could somehow or the other escape and get away. But you are worried if you're flying 8-foot helicopter that weighs 55 pounds, that it might get to downtown, right? So big issue there. More high potential, more potential energy. I don't have to tell you about that. And then what that means is higher level of cert required. The ground vehicle world is a little bit confusing, right? I mean, confusing. Actually, Dirk told me this great story of how cert worked by when they went to California was having lots of rules, so they went to Nevada, and then the people in Nevada said, okay, you're very welcome here, and then California said, wait, no, we want this back here, we'll change our rules again. No. Okay, FAA, no, not happening. FAA has a completely different idea okay, we'll see what happens, that kind of thing. Okay, so a few things are different, a few things got easier, a lot of things got much more difficult. But here's the thing, what's the more interesting part is how is it the same? Okay, and I'm gonna sort of push one side, which is, lots of technology is the same. I don't want to show you any videos. I want to give you an idea of what I think is the same, is that we do something at a university, we show this, first flight here, this, underground, overground, whatever. We're doing this, flying a long distance, but we've got the same problem of how to make something technology commonplace, which is any technology has got to be capable, it has to be reliable, it has to be viable, economically, it has to be easy to use. Then you start to think about, how's this going to work? It's going to become a product, right? And I see a lot of the ground vehicle people are struggling with this, right? If you have a vehicle that costs $200,000, hard to make it in a taxi. How are you going to make it into a taxi that rivals somebody else? Well, it doesn't quite work until it all works. Right? Until you have 1 million of them on the road, Elon Musk notwithstanding his estimates, well, it's going to be a while. So this is a problem that everybody has in our world, and I'll confess this is an issue. So the thing that I've been thinking about is like, how do you do this adoption? And it's the same. And so I'll give you some thoughts on this and there. So the idea here is, let's go first principle. Why do automation? We're looking at dull, dirty, difficult, dangerous. Everybody's been hearing this for a while. This is the idea. This is what gets people thinking about automation. There's some hazard, there's some efficiency. So I've been thinking about how does a sequence work? Lots of people try lots of things. Many things die on the vine. Many things don't go forward. Well, it starts in some place, which is with applications like this. Go into a nuclear reactor. Go into a difficult environment like the kinds of things you've been seeing. Go to another planet. That is sort of like the place we start, right? Early adoption, higher tolerance for risk. And then you get to this part, which is this dull and dirty, difficult kind of thing with this kind of world, where things are large, the huge leverage for automation. Cost is important, but because of scale, and it's about dull and dirty and difficult, when the basic work's been done, then you get this. And then if you have this virtuous cycle, you get this technology that becomes, has an economy of scale, and then it has ease of use. Okay, so we're getting close. I was really interested in Todd Yoakum's comment about how he uses a Tesla on the highway, but never in the city. This is a fascinating kind of a take from somebody who's been there. But the question here is, how hard is that problem? And are we going to be in the trucking world for reasons that, there's just better economics there? Okay, so shouldn't be surprising. We think about this in the air vehicle side. Start off in a medevac kind of thing, difficult battleground, dirty, difficult, dangerous. And then, there's the dull part, which is large scale, that you can move A to B for a while. And then there is some sort of economy of scale, ease of use kind of thing. When the technology has been proven, then we've got some case to make that, okay, we've been flying for 1 million hours. FAA, please let us do this and something other than trial. But this is a sequence. So my point here is, I've been struggling on why can't we go to these commercial applications. This is why. So just a thought here. We've been seeing things start and fail, and my take here. Okay, I want to keep everyone on time. I'm going to stop here. Please feel free to talk to me later about these things. Lots of media on the web. But I want to switch to a different thing. This is a point of pride for me, and also a sign of where we have been and where we've come. So, this world of ours that we started a long time ago, I was on a plane with Red when he said, hey, how about field robotics? What do you think? We were this construction robotics lab. We were on our way back from Peoria to Pittsburgh. He said, field robotics. He said, like, field robotics? That's kind of not right. We had some people say field robotics. They made fun of it. But okay, that over time has become a thing, and more than a thing. A couple of journals later, now we have a transaction on field robotics. In some sense, as a gray hair or a guy with no hair, I think this is like a real point here. So this is now we're almost passé. There is a journal where this kind of stuff that you've been talking about is you can write a journal paper and the IEEE blesses it. Okay, thank you very much.
All right. So my name is Max Likhachev, and I'll give a kind of a short presentation or talk on the role of planning in modern systems. I wanted to talk about that for some time. So as many of you know, my group works on planning, developing planning algorithms, and really kind of applying to a broad set of robotic systems, anywhere from outdoor navigation to aerial vehicles to manipulation and so on. And a very common question that I actually get nowadays is, do we even need planning algorithms given all the advances in ML? And given that I do get this question quite often, I decided to put a quick talk on kind of that demonstrates my view on this particular question. So a while ago, back in 2000, when I was a student and I was young and I was dumb and I was broke, all of those things, I was actually working on behavior-based robotics. So for some of you, probably many of you know that behavior-based robotics kind of back then was quite popular, and the view that it has taken is that you don't actually need any planning. Planning is expensive, you don't need to do any sort of deliberation per se. Instead, you want to pre-build a collection of behaviors, combine them in a certain way, and that will do what you want the robot to do. And it actually worked pretty well. So in kind of when navigating through forest, in sparse forest, you could actually see the vehicle going very nicely, avoiding trees and so on. But then whenever you get to the situation where you have kind of like 3 or more trees creating cul-de-sac, it gets stuck there. And you're just sitting there and it looks really miserable, kind of trying to navigate away from those more than 3 trees. So it was kind of quite frustrating. And I was taking a class on behavior-based robotics at the same time. And one time when I kind of came to the class, there was a bunch of brochures all over the class. And those brochures were from the previous class. And that previous class was on financial planning, just nothing to do with robotics, it's just on financial planning in your life. And those brochures, they all had a big title that said, "Lack of planning is hazardous to your future," which was very ironic, given that the behavior-based robotics was preaching the fact that don't do any planning. So that's kind of came somewhat of a revelation to me, combined with my experiences of doing this behavior-based robotics. I decided, no, that's not what I want to do. I want to do planning. And I think the deliberation is really important. It's like a key to robotic systems. So after that, I spent quite a bit of my career on, I don't know how to disable this thing, I guess it doesn't work. Anyway, on developing planning algorithms that do take real-time constraints into account, in particular, a lot of anytime planning algorithms, which try to generate the best solution they can within a given time constraints. It was applied to a variety of different systems, anywhere from the urban challenge vehicle to the driving the, I guess it doesn't play that, but anyway, to driving the sports vehicle, to aerial vehicles on the bottom, flying through indoors and outdoors. Now, more recently, kind of going with the same flow of trying to develop the algorithm that satisfy real-time constraints, we also have developed a class of algorithms called constant time motion planning. Those are the algorithms that are targeting semi-structured environments where you have a lot of kind of a knowledge about the environments where they're operating, like, for example, manufacturing and so on. And there, it's kind of silly to do online planning to solve those similar problems over and over again. Instead, it turns out that you can actually pre-compute certain data structures that allow you to guarantee the ability to return plans within user-defined few milliseconds. That gives you the reliability, which is really, really important for the systems that go into production. So you can actually reliably say that your planner will return the solutions within a few milliseconds. That allows you to build those much more reliable systems. Now, kind of going into the, thinking about going into the future, and given all the advances in machine learning, obviously one of the biggest flaws of planning is the fact that it relies on the models. And when we're talking about interaction with the world, when we're talking about interaction with people and other agents, there is a lot of brittleness of those models. Those models inherently are not correct. They're quite noisy and so on. It's very hard to actually predict how the people will react to the robots and so on. So the learning on that sense, of course, gives us a huge advantage. It does, from the data, actually get a much better model. On the other hand, when we're thinking about planning and planning long horizon trajectories, it's not really scalable to think of learning that will be able to scale to those long horizon planning from data. So with that in mind, kind of the flow that we've been thinking about is that we really need to have, really need to think about the algorithms that combine planning and learning within a single algorithmic framework. And that helps you to scale up learning to the longer horizon thinking. So we've been kind of doing that in the context of multiple domains, but one of them is multi-agent pathfinding, where you have lots of robots, up to 1,000 of robots. Those are, of course, driven by things like Kiva, Amazon-like systems, and so on. And if you take techniques from ML, like a machine imitation learning, which has been popular with application to the map as well, you do get some kind of reasonable performance. But on the other hand, when you look at it, the scalability of those methods, especially with respect to those a number of agents, you can see that the success rate drops quite rapidly. So you can see that this kind of a diagonal line, as you go more and more agents, the success rate drops close to zero pretty fast. And of course, from a production perspective, that's not really kind of in any way gives you reliability that you want to have. Now, if you take the imitation learning and you actually combine it with planning and do it in a way kind of where you have planning handling the difficult cases where the learning gives you the solutions to the easier one, then the scalability of this approach is dramatically better. So those are the things that are shown in green. And really kind of the observation that we have made is that this combination literally crushes the pure ML-based approaches, even when relying on much less data for training. So kind of that's been one of the kind of key directions that I think are important to explore, which is the algorithmic combinations of ML and planning together. So the kind of wrapping it up, I do think that lack of planning in robotics would be very hazardous, and it's very critical to the robotic systems. The kind of going forward, I think it's important for us to think about how planning can be integrated with learning in one single algorithmic framework, and that gives you the scalability, and it also allows you to have a much more rigorous safety guarantees on the overall system. At the same time, I do think that it's important for planners to be able to reason about the scalability of the kind of how far in the horizon they do planning, so that they automatically go from a short-term planning to long-term planning, and it's not predefined, but instead it's kind of done automatically. So with that, I just want to finish. And of course, thanks to all my students and the funding agencies. Thank you.
So I wanted to start a little bit more on a meta level, because it's been really nice to kind of have all these generations of people together here, and so I'll start a little kind of going back and then going forward. And so I wanted to kind of think about I've been thinking a little bit about like what kind of influences our research and some of the things going forward, and how has that influenced us. And I think a lot of that has been driven by like my advisor, Red, Sanjiv, Reds and Takeo, and all this kind of previous generations. And I think a big one is not being afraid of just trying these things out, right? And I think Sanjiv also mentioned this, right? Like we didn't even know that we shouldn't be doing these kinds of things, right? And I think that kind of mentality is still kind of living on, and similar, this kind of test early, test often. I think on Monday I visited Carnegie Robotics. John Bear said, we test early, test often, right? And he's really the master of testing in terms of components, right? So I think that was one of the big influences, and part of this, for example, was the DARPA Sub-T challenge, right? Here's more of the kind of drone view of things, since this is the aerial session. And so you can kind of see all these various ideas come together. Flying underground, smoke, everything has to be autonomous. Same things that we've been seeing. Seeing the symposium today was also really interesting to me to see how there's a little bit of like a Groundhog Day moment, right? we keep on redoing the same things over and over, but hopefully every iteration of when we do this, we're getting better at these things, right? Doing thermal, depth estimation, stereo, imitation learning, looking at the horizon, learning what we will be doing, all these same ideas, right? And then since it's just the Raj Reddy Symposium, I looked at some of the old talks from Raj Reddy, and I think one of the things that stood out to me is, this kind of attributes of intelligence list that Newell had, and, it's looking at, we're still working on a lot of these things, and, trying to take these attributes and, trying to get closer to these ideas, right? So trying to learn from experience, we wanted to operate in real time, tolerate error and ambiguity, using symbols and abstractions to reason. And so when we do projects, I think this is not news to anybody in here, but I think it's good to think about is how do we go. One of the ways we do a lot of problems is think about, again, what is the application and how do we solve this the best way, right? And so that's kind of the one way where we often discover the actual problems when we do this. The other way is to go, sometimes we see some new research and that creates some new problems. So one of the directions we've been pushing since is to try and develop this more unified approach. There's mainly for efficiency, some of it is for efficiency, some of it is to also allow new tasks. And so that is to try and have this unified representation to then reason over, right? And I think similar to a lot of the previous talks, right, we're also thinking more about a modular approach that has some reasoning in it, in addition to some combination with learning, right? So the types of applications we're looking at, there's a wide range of, going from wildfire mapping to off-road driving to flying in airspace, information gathering, but similar ideas that kind of go through these various applications. One in particular, oops, is that? Okay, oh, sorry, yeah. One in particular that I wanted to highlight that we've been working on is a larger collaboration in RI is on the DARPA Triage Challenge. So this is a collaboration with the people at the bottom here. And so you could think about this as a team of pre-first responders, right? So you have these robots that you send in before the first responders arrive to really give you different information that you need to make triage decisions. And so you're trying to do things like estimate your respiration rate based on a video, estimating ocular alertness, heart rate, and verbal alertness, for example, in addition to a lot of the robot autonomy pieces. And so there's still a lot of the same questions that were brought up on the earlier talks are still active now, right? So how do we coordinate these teams of robots to save the maximum number of lives? How do we perceive the world in 3D and 4D? How do we maintain safety in degraded conditions? And how do you interact with these teams in a natural fashion? And how do we accurately measure and evaluate relevant data to enable these kind of triage standoff decisions? And so, I think there's, just to kind of maybe finish off the talk, what I wanted to kind of call out is that there's actually a pretty large number of students in the audience here also, which I'm really happy that they all came down here, which is in some sense, the next generation and I think it was really good for them to kind of see, get the historical perspective. A lot of them are like, oh, I thought this was new, what I'm working on. And so I was like, no, I already knew about these ideas and I just told you to do it again. So I think maybe you guys can quickly wave and you have a pretty good representation, I think, from a lot of people from Squirrel Hill here. So yeah, so thanks everybody. That's it.